Yeah. Share the screen. All right. So this chapter is not introducing new concepts. We're looking at specific applications of Newton's laws. So let's jump into the first slide. We have already discussed a bit about this in previous classes, you know, to solve our problems, to do some examples. So let me refresh the concept of equilibrium. So an object is in equilibrium when it is at rest or moving with constant velocity. And of course, in an inertial frame of reference, meaning that that frame is not accelerated. Okay. So we consider only the equilibrium of an object that can be modeled as a particle. So for us right now, objects are particles, as we've been working through the past classes. So if we apply Newton's first law, we can say that the net force is equal is 0. So if we have that, then we have an object in equilibrium. And of course, if we have a, let's say, 2 dimensions or even 3 dimensions in our problem, then we can say that the components of that net force of that sum of forces will be 0 too. So each of the components of the projections into the axis has to be 0 too, even meaning that we'll have the component of velocity constant in each of the axes, or 0, constantly 0. Okay, so that's one aspect of taking a in consideration that the net force, you know, is 0. So if we don't have equilibrium, then we have some kind of dynamics in our particle. So in dynamics problems, we are applying Newton's second law to objects in which the net force is not 0. So remember, when our net force is not 0, that will imply that we have some kind of acceleration. And that acceleration will be parallel and in the same direction as the net force is being applied to that object. So these objects are not in equilibrium, and then they are accelerating. So we have this relationship here, which is the net force equal mass. Remember that we define mass as the ratio between the net force and acceleration. So we have a mass here, which for us will be constant, and it's a scalar, of course, and these two are vectors. So we have a vector times a scalar, vector times a scalar. So the force and the acceleration are parallel vectors with the same directions, because of course we will never have a negative mass, at least in our classical mechanics problems. And so we can apply the same reasoning and project into the axis of our system of reference, and we will have the acceleration on each of those axes and the net force on each of those axes. So same reasoning, but now we have a result of net force which is not 0, meaning that the particle has dynamics. The particle is it has acceleration, right? So remember, in equilibrium, the particle can be moving. So this is let's say conceptual question. If you have equilibrium, the particle is still, not necessarily. So the particle could be subjected to a constant velocity. So that will be equilibrium too. Okay. Equilibrium, of course, we are talking about equilibrium of forces, not of let's, I don't know, state it as equilibrium of movement. So like, that would be something that's not moving, but no. Okay. Okay, so let me make a stop here before we move to friction, and let's take a look at problem section 1, problem 7. So please go to that section, that problem, and let me share screen on the tablet. Sorry, on the tablet. And any questions about this two main considerations, equilibrium and dynamics? Please please go ahead if you have any questions. All right, let me stop sharing here and share with the other device. All right. So let's see, we have problem I7, which says it has a block there, which is attached to the wall on an inclined plane. So it says the object of mass m equals of mass m that equals to 4 kilograms is in equilibrium on a smooth inclined plane. That means that there's no friction there. So now we'll see the coefficient, the friction coefficient is 0. So there is no friction here. And the block is suspended from a rope with tension T. The direction of the rope is parallel to the plane. The value of the angle theta is 20 degrees. And then we need to draw the free body diagram, find all action-reaction pairs, then find the value of the tension exerted by the rope, and then find a value of the force that the object exerts on the inclined plane. So let's start by showing making a diagram of this problem. Here, so we have a plane. With some angle theta, a block here, and a wall, and a rope. So this is M, this is 20. All right, and there is no friction here. We'll see this mu in the next slides. So what's convenient here? Let's just think about it. How do we establish our system of reference? Well, the most convenient thing to do would be to establish the system in the solidary to the axis that the block could move, right? So although we know it's in equilibrium, so if we have equilibrium, we know that the sum of forces should be 0, right? So let's say that we establish our system of reference in the same with the x-axis, the same direction as the plane, and the y-axis pointing perpendicularly to the plane. Okay, so if we do that, then we can do the free body diagram of the block. So let's say we have the block here, and we have the block. I mean, the first force that comes to our mind is the weight, right? Because the block has mass. Then the other obvious force there is the tension that the rope is exerting. We call it T. And then we would need to add the normal force, which in this case will be perpendicular to the tension, because the normal force is perpendicular to the floor, and it's telling us that the rope is parallel to the inclined plane. Okay, so we have that there. Then we would need to, in order to get the action reaction pairs, we would need to draw the normal there. Get some colors. Okay. Here. Oh, it's not picking up the colors. Sorry. Yeah, something wrong with the pencil. Let me close the app and open it again. Let's see. Whoa. Okay, it seemed that I have lost that slide. So let me just real quick get the drawback. So we have the plane, block, wall, and theta, system of reference, X, Y here. Free body diagram. We have the weight. We have the tension. We have normal. And I wanted to use some color to draw the reaction pair of the normal on the floor. Would be N prime, and the reaction of the tension T prime on the rope. So let's say this is the rope here. All right. And let's not forget about the weight. Every time I do this, this is the earth. Let's use another color. That would be weight prime. So those are all the action reaction pairs that the problem is asking for question. Yeah, for question 1. So we have the free body diagram and we have action reaction pairs. All right, so the forces that the block is subject to are the normal force, tension, and weight. Is there any doubt about that? So we don't have friction. Remember, this is a frictionless plane, so there is nothing else to take into account in this time. All right, so let's take a look at the equations that we get from this situation. So if we let me draw the system of reference bigger. So you have X, Y, and then we can draw the forces that are here. So we have tension, we have normal, and we have weight. So weight, it's always pointing down, remember that. So this angle would be theta. It's the angle of the inclined plane. Can everybody see that? Oh, because error is frictionless, because it states that on the problem. It says is on equilibrium on a smooth frictionless inclined plane. It's because the problem says it. Of course, we will have some problems with friction, but for now we don't have friction in this one because we'll see it at the second part of the class. Right? Cool. So any doubt about that angle? So if it's basically you get that angle by rotating a horizontal system of reference, and of course you're rotating it. You can see it here. This is theta, right? This is the angle that the plane is inclined. So that angle will translate here to have that angle on the weight. Okay. So that angle will let us calculate. Let me just make it cleaner. So that angle will let us calculate the components of the weight in each of the axes. On the x-axis, on the it's a bit longer, on the y-axis, and we would need those to write the equilibrium equations to figure out how much is the normal and the tension, because that's the other question. The question says find the value of the tension and find the value of the force that the object exerts on the inclined plane. So which is the force that the object exerts on the inclined plane? It's not the normal, it's n prime, it's this one. Okay, so that's the green one is the force that the block is exerting, which in module in the value of the modulus of the vector is the same as the normal. But being strict, the normal is not the force that the block is exerting into the plane, and that's a conceptual differentiation, right? Okay, so let's do some quick calculations here. So just one more thing to clear. So the free body diagram is what we have here, right? So this is not the free body diagram. We don't have axes in our free body diagram. We just have the particle and the forces that are acting there. And after we have our free body diagram up here, then we can put the forces in our system of reference and then start doing calculations. So please, when you're asked to get the free body diagram to draw that, please do this. You don't include the axis in there. Your system of reference is independent of the free body diagram. Okay, so after you identify the forces, then you choose a system of reference, and then you start doing the calculation for the problem. So this is totally independent from the system of reference you're choosing. Those forces will be there no matter your coordinate system. All right. Okay. So what we can write here is, the two net forces in each of the axes. So let's say Fx equal T minus weight X, and that should be 0. So we're looking at the x-axis, right? So we have tension pointing to the positive direction, and we will have weight X pointing to the negative direction. So we have a minus there. All right. And if we have the other, we would take a look at the y. We'll have n minus weight y equal 0. Because again, we'll have the normal pointing up, and then we will have weight y, the projection on the y-axis, pointing down, which is negative in this case. All right, so we have that system, let's call it system of equations. And weight x and weight y, we can express them as weight x equals weight sine of theta, and weight y equal weight cosine of theta. All right, so we're just applying trigonometry there. So if we take a look, weight x is on the opposite leg of the triangle, so it's opposing the angle theta, and weight y is adjacent to that angle, so we use the cosine. So here you can see another example of how sine is being used to calculate the x component, and cosine is used to calculate the y component. So again, there's no reason to think that cosine just applies to x. It depends on the trigonometry of the, or actually the geometry of the system of reference you're using. Okay, so always be don't go just blindly applying cosine for x and sine for y. Reason the geometry of your problem. Okay, cool. So any questions about that? Is that clear? Oh, I have something in the chat here. Oh, it was Aaron's old question. Okay, so let me continue. Yes. Okay, so from this, what we can do is say that from the first equation, we can say, let's call this 1, let's call this 2. Yeah, will you show us a problem after this that shows a different application of sine and cosine? What do you mean different application? Like, you know, calculating the components? I mean, that's the only application for now. You mean like weight, if we have to calculate the x with cosine and the y with sine? It's just a matter of the triangle you're using. Okay. All right, so from 1, we can say that P equals weight x. All right, so this is equal to weight sine of theta, which is equal to, remember, mg sine of theta, because the weight is calculated as the mass of your object multiplied by the acceleration of the gravity. Nathan, should our goal when establishing a frame of reference be to plot the unknown forces on the axis? Well, yeah, you will need to do that to be able to be consistent when you're calculating the net forces, right? So you need to do that to calculate the net force in each of the axes. But yeah, you need to establish that system of reference. If not, you wouldn't be able to balance, the weight with the component of the weight in the y-axis with a normal, and then the component of the weight on the x-axis to the tension. You need to do that in order to know how the block is maintaining this equilibrium state. I don't know if that's answering your question, Nathan, if you were. So should we avoid having to find components of unknown forces? Of course, if you can place, you know, the more forces you can place parallel to an axis, the less calculations you gotta do, right? Because let me just sidetrack real fast here. So we imagine we just established a y-axis, you know, solidar to the weight, then we would have this, right? We would have tension here, and we would have normal here, and then we would have x pointing this way. So we would need to calculate the components of the normal, the components of the tension, and then we would only have the weight solidar to the y-axis. So we would need to do let's say two more calculations. You can, of course, you can solve the problem using this kind of system, but it's not, you know, the optimal way to do it, because you have to perform more calculations, but it's perfectly doable. All right. Yeah. It's just a rotation of your system of reference. That won't change the fact that you know the angle and that you know the weight. Okay, so let's continue here. So we have that tension equals mg sine of theta, and that's actually what we want to know. So we can replace our data there. So kilograms, 9.8 meters per second squared, sine of 20 degrees. Yeah. And that will give us, if I got it right, 13.41 newtons. And that's the tension. Okay. So the tension is basically balancing with the x component of the weight. And from equation 2, we can say that the normal is equal to the y component of the weight, which is weight cosine of theta. And again, same reasoning here, mg cosine theta equals 4 kilograms, 9.8 meters per second squared, cosine of 20, and we get 36.84 newtons. Normal. But let's make some a distinction here. As we mentioned before, the problem is asking the force that this block is applying, you know. So let's go back. So at first it said find the value of the tension exerted by the rope. So we know that the rope is exerting a tension on the block, which is the block, the vector t. So here we have the modulus, the modulus of t, which is 13.1 newtons, and that's the force that the rope is exerting on the block. So the second question is asking the force that the object is exerting on the inclined plane, and that force is not strictly the normal, but as we said before, it's the prime. So that n prime, if you want to, let's do it with tension two. If we want to give the vector t, it will be equal to, so remember we have unit vectors, of course, y, I, and j, both unit vectors. So tension will be 13.41 newtons times vector I, and n prime, right, would be, in this system of reference, would be pointing down and would be equal to that modulus of n. So it will be, let me zoom out, it will be 36.84 newtons J, but with some negative sign there, right? Because we are giving this force, okay? The force that the block is exerting on the plane. Okay, any questions about that? So it's a fine distinction there. So it's not asking for the normal, is asking for the n prime. So the reaction force, which is being applied to the floor, to the inclined plane. Yes. So Varsha, the n prime is pointing down because it's so you have our action, let's call it action, is the n force, which is the normal that the floor is applying into the object to support it, right? So that's pointing up, let's call it, in the y direction. So it's pointing up. And then the reaction force, by Newton's first law, third law, we know that the reaction force will be acting the same line of action, but it will have an opposite direction. So n prime will be pointing the opposite way of n, and it will be taking action on the floor. So n prime is the force that the block is exerting on the plane, on the floor. Is that clear? All right, thank you. Okay, so is there any other question about this problem? I think we covered it. We covered all the aspects. And if there is not another question, let me move to another problem, which is problem I-10, section I, problem 10. And let's read the problem. So it says a man of mass 70 kilograms is standing in an elevator. What force does the man exert on the elevator floor when it's moving? So in this case, we will have a particle, the person, an object that it's moving, right? So then we would need to be careful when applying the net force and applying Newton's equation here, because from a quick glimpse, we can say that if we have acceleration, if we have a net force that's different from zero, we will have some kind of acceleration. Okay, so let's establish our system of reference pointing up, which is the most intuitive thing to do, because the elevator goes up and down, and we have let's draw that. We have the elevator, and we have a person there. Like person, and let's draw the free body diagram for that person. So we have weight pointing down, normal pointing up. So the floor is supporting the person with force and normal, and then the person is pushing the floor down with n prime, and we have weight prime on the earth. Okay, so same drill as before, pretty straightforward that. And so let's take a look at the question. So it says, what force does the man exert on the elevator floor when something happens? So we're asking about that n prime force, right? So we know that n prime, n, let's write it like this. The modulus of n should be equal to the modulus of n prime. So for the sake of simplicity, we just write the letters, right? Like this. We ditch the arrow, well, the segment up there, and we just ditch the bars. Okay, so we know that those forces have the same value, but opposite directions. So if we can calculate n, we can calculate n prime. Okay. So for the first one, it says the elevator is moving upward with a constant velocity of 10 meters per second. Let's take a look at that. We have a velocity equal 10 meters per second. Let's get our unity vector there. J there. And if we write the forces for the y-axis, which is the only one that we really care here, is we have n minus weight equal 0. Okay, because we have constant velocity, we don't have acceleration, so we simply can write n equal weight. Okay, and we can we calculate that? Can we calculate that? Yes. So that's mg equals, let's just replace the man weigh, the mass is 70 kilograms times 9.8 meters per second square, and that's given us, I should have moved that to a better place here. And that's given us 6.86 newtons. Okay, so n, that's the magnitude of a normal, and then we can say that the normal is equal to the magnitude of n prime, so n prime is equal to 686 newtons. Any questions about that one? Okay, so let's take a look at case B. So for case B, it says it's going upward with a constant acceleration of 1 meter per second square. So if we have that, if the thing is going up with acceleration, then we cannot say that net force on Fy would be 0. It would be something, right? So again, we write same thing because forces haven't changed at all. So you have the normal, the weight, and this is equal to m acceleration on the y-axis. And that's a positive acceleration because it's going up, right? So it's going to be positive, that If not, we would have a minus there. Okay, so it's pointing up. And if we calculate that, we would have n minus mg equal may, and that's given us for n, we can write may plus 9.8 meters per second squared, and n will give us 756 newtons. Okay, so this is 1 meter per second square, and this is 70 kilograms. Right? Okay. And then I want you to think about the question C, but now we will have a you know, it says a downward, it's going downward with constant acceleration of 1 meter per second squared. So just think about that one, and we can take a look at the next class. Right, or of course ask. Yes. Let me move to the PowerPoint. Let me go back, and we can continue with friction. I'll just get that there. Okay. Right. Let's share some here. All right, so for the last part of the class, we will go over some more slides about Newton's applications. And let's take a look at friction forces. So we just mentioned a couple of times what friction is. So when, of course, you all know what you have a notion of what friction can be, but now we will characterize that from a physical point of view. So whenever two objects are interacting by contact, we will say that that interaction, it's described in terms of contact forces. So we have the normal as a contact force, for example, and we've seen that it arises from the fact that you have something that's, you know, in contact with a surface or another object. So you have that normal force. And let's see how friction arises from this kind of interaction. So just think of a world without friction at all. Of course, we wouldn't be able to perform day-to-day activities, right? Because for friction, in order to turn your car, you would need friction in order to, to make a plane fly, to use a parachute, to just just walk, right? To get some kind of locomotion, it will be impossible without friction because you will just sliding everywhere. So friction is important, and it's important to take it into account even at the most basic level of physics. And we have two kinds of friction forces that are dependent of the type of the kind of scene that we're looking at. So we can have kinetic and static friction. So when the object is moving in some direction, then we will get a friction force, which is it's pointing on the opposite direction of that movement, and which is always parallel to the surface. Of course, we're talking about a movement which is taking place when the two objects are in contact. So let's see this example here. So we have our normal force that we've defined before, and then if there's friction between these two objects, then if we're pushing or pulling to this side, then a friction force component will be appearing, pointing to the other side, so counteracting that pull or push. So if we want to define a contact net force, that would be the sum of those two forces, right? The normal force and the friction force. Okay, so that's when we're talking about contact force globally, we are talking about normal force and friction force, because those two forces are due to the contact between those objects. Okay, so let's define the kinetic frictions. So if you ever try to push a chair, you'll notice that if you exert a very little force on it, it will not immediately move, right? So if you keep increasing the force that you're applying, it won't move until a specific point that you'll break that inertia of the object being still, and it will start moving. And once you are able to move it, then you'll notice that that movement is easier to achieve. So it seems that there's less resistance once the object is moving, and that's due to the fact that the friction changes if whether the object is moving or the object is still. So the kind of friction that acts when the object is sliding over the surface, which meaning that it's moving, it's called kinetic friction force. And we use letter K to symbolize that. So Fk would be the kinetic friction, and we will only have it when the object is moving. So the magnitude of this kinetic friction is found experimentally to be proportional to the magnitude of the normal force. So please take a look here and see that this is not a vector equation. This is a scalar equation. So we have mu, which is, remember that I mentioned it a couple of times before when we said that we had a frictionless plane, the mu was 0, so no friction. If you have no mu, you have no friction. That's straightforward from this equation. So mu, which is a number, multiplied by n, which is the magnitude of normal force, and we have the kinetic force. If this thing here would have, you know, the vectorial notation would have that would imply that the friction force is parallel to the normal force, which is totally not. right? The normal force is pointing this way, friction is pointing the other way. So those two are perpendicular, okay? So this is a scalar equation. Just have that in mind. And again, this mu sub k, this mu k kinetic friction coefficient is it's a property which arises from the type of the type of materials you're dealing with. So if you have two materials that are being in contact with each other, then you'll have a specific mu k. So that's determined by the the nature of your surfaces. So let's keep defining this. Well, easy example. So this is why we can say that it takes more force to slide a full box of books. I mean, something that has more mass, because the fact that having more mass will determine a bigger normal, and that will give us a bigger friction force. So things that are heavier are harder to move when you have a contact between the two surfaces. The more slippery the surface, the smaller the coefficient, of course, because we will have less friction. And as I said before, this is not a vector equation, because those two are always perpendicular. You know, Fk and N are always perpendicular. So if we take a closer look to this, we can come up with an explanation. Let's say for the friction on a microscopic level, because you can think as this as two jagged surfaces which are being in contact with each other. So you'll have, you know, bumps and valleys here which are interacting with each other on a microscopic level. And of course, if we go too deep into matter, then we will know that this intermolecular forces have an electrical nature that creates those bonds when they come into contact. So, but from a less if we zoom out, let's say, from a microscopic level, not into the molecular world, we can say that we have two jagged surfaces which are coming to contact, and of course they are you know, getting this kind of link with each other, and that link would be broken when you're sliding surface, let's say the block, over the floor. So you'll break those links that are formed, and then you'll have a friction which is due to the movement, and that intuitively you can think that it would be smaller than the static case. So as I said before, we have this kinetic friction, which is not perfectly constant, because of course the topology of these two surfaces would change with time as we are sliding one object over another one, over the other. All right, any questions about kinetic friction? Because now we're gonna jump into static friction. All right. So for static friction, it's kind of tricky to understand it, but we can have friction even when there is no relative motion of the object. So as I said before, if you try to slide a chair, or let's say a box across the floor, the box will not move at all because the force exerts an equal opposite friction. And as long as you keep pushing and increasing the force that you are exerting on the block, then the static friction force will increase until some breaking point is reached and you start moving the box. Okay, so same as before for a given pair of surfaces, the maximum value, so just notice that the maximum value of the static friction will depend on the normal force. So we can say that the maximum value of the static friction equals to the static friction coefficient and the normal force. So we have the same expression, but now we're using a static coefficient to get the maximum of that static friction. So this is not exactly calculating the static friction, it's calculating the maximum that we can have until those bonds are totally broken and the object starts moving with kinetic friction. So let's look at an example here. So if we have the box resting, we have no force, nothing, just normal and weight. So this thing is in equilibrium. And then what we do is we start pulling to the right with tension. We are creating a tension here, but the tension is too weak to actually move the force because we have friction here. So this thing is still in equilibrium. And as we know, for equilibrium, we need to satisfy the condition that the net forces on the axis are 0. So of course, the net force here is not on the y-axis, not changing at any case. So we have the weight, the magnitude of the weight equal to the magnitude of the normal. That's for the y-axis, and for the x-axis, here we have no force at all. So sum of F equals 0. Here we have tension and the friction that it will need to arise, right, to keep that balance on the x-axis. So if I tell you I'm exerting a force T, and the object is still in equilibrium, it still doesn't have any acceleration, so this Fs, static friction, has to be equal in modulus to that T to keep the box still, right? Not moving. If we continue making this thing, so let's just say that these static friction will be smaller than the limit that we have here. So at point A, we have 0 friction, nothing. At point B, we are pulling from the side, so the friction appears and keeps going up, like this curve. Well, not curve, straight line that we have here, right? Which is dependent of this T force. So at a breaking point, we have enough tension to balance with the maximum static friction that we can have, which is mu static multiplied by n. So at that point, we are standing here. The friction is maximum on the static condition. And if we keep pulling with some, bigger tension, then that relationship will break, and then we'll start moving the object, and the friction will the actual graph of tension friction. We'll see this. It will go down here, and then we'll have normal. We'll have a constant, let's say, roughly constant kinetic friction, which is not strictly constant, but it roughly constant, as we said before, kinetic friction, which will be equal to mu kinetic multiplied by the normal. So then, if we want to keep constant speed, we would need to decrease T in order to match Fk and keep the and keep the equilibrium condition in this case. If we keep pulling with the tension equal to the maximum friction, the static friction that we had before, you know, in terms of modulus, then we will start accelerating the object. Just think about that, right? If we have t equal in magnitude to fs, and we know fs has a maximum point, and then all of a sudden when the box starts moving, it decreases, but we keep pulling with the same t, then we will create a force, a net force pointing to the right, and that will give us some acceleration. But in this particular example, we just decrease t to match fk, and then we'll have constant speed. So the box will move constantly with constant velocity and at equilibrium to the right. This is just a way to show how the kinetic friction and static friction arises from a situation where you're pulling that object. Well, it could be a push, it could be a pull, doesn't really matter. The matter is that the box is sliding over that plane. Oh, all right. Any questions about friction? Okay. Let's stop here for today, and tomorrow we will refresh. We'll go back to friction and do some problems about it. All right. Anything else? Let's just stop the PowerPoint here. Any questions about the course, about how we're doing? If not, let's just stop recording. And thank you guys. And